Welcome. So today we're doing combination reactions where you take two different things and you combine them together to make one thing. In a combination reaction, you will have some element, often it's going to be a metal. You're going to react it with some other element, often a nonmetal. And in the case of metal and nonmetal, electrons are transferred from the metal to the nonmetal so that you can make an ionic compound. You're going to have some cation and some anion as a result. By making a cation and anion, that allows you to make an ionic bond and connect things together. And a great simple way to come up with that formula is to look at the periodic table. So you look at the periodic table and you look for the common charges. Like if we were combining aluminum with oxygen, we know that aluminum usually forms 3+ ions, oxygen usually forms 2- ions, and we would try to find the correct ratio between the two elements to make a neutral. Okay, so a great way to do that is this crossover method to get those subscripts, so long as if you remember to simplify X and Y if that is possible. For the subscripts on the reactant side, it's going to be a 1 for most things like metals, for example. But plenty of times these reactions will involve these 7 diatomic elements: H2, N2, O2, F2, Cl2, Br2, I2. All right, these are your 7 diatomic elements. In their elemental state, you find them as having 2 atoms of the same element. All right, so a quick way you can learn those is to go to your periodic table, make some boxes around these 6 elements, and then here's number 7. The way I visualize these 7 is, to me, this looks like the number 7, even though there's just 6 here. So 6 of the 7 looks like the number 7, and then we have the 7th one out there. This gives an image in my head of someone playing hockey, and then their hockey stick went high. Maybe they did high sticking, and then that was the puck flying away. That's my visual. But again, at the end of the day, if you have any of these elements isolated, give them a subscript of 2. Okay, again, on the reactant side. If we're talking about the product side, this does not apply at all. All right, and there's other elements out there that might have different subscripts. Sulfur is often an 8. Phosphorus is sometimes a 4. And carbon, there's nanoforms such as carbon nanotubes, carbon buckyballs. All right, C60 is a buckyball, but we're not going to worry about that here. We're mostly going to be here. Maybe we'll work in a sulfur example at the end, though. That one's like somewhat common. All right, so let's get started. So this is our first example today, example 1. So a common thing to do is they'll give you a metal and non-metal, like we said earlier. In this reaction, they already wrote out the reactants, so they're leaving it to us to predict the products and then to balance the equation. So just to remind you of the steps for a reaction. Number 1 is products, and number 2 is to balance. Okay, so we have to figure out how these combine to make a neutral ionic compound. So using our template from earlier, we're going to go to the periodic table and find the common charges for aluminum and oxygen. All right, so aluminum is in the 3+ column. If you haven't done so already, go to your periodic table and mark it up with the usual charges of 1+, 2+, 3+, 4+, and then 3-, 2-, 1-, 0. Okay, so we needed aluminum in the 3+ column and oxygen in the 2- column. All right, so I'm not going to put in the products yet. I'm just trying to figure out what I'm making. All right, so we're doing some crossover. And this is a quick way to find a ratio of elements that makes everything neutral. All right, and so now that I know what I'm making, I can go ahead and put it in. All right, once you have your products, it's time to balance the equation. Remember that you can change coefficients. Those are the numbers that go in front, but you now have subscripts off limits. That 3, that 2, that 2, you know, this is a 1, but we don't write it in chemistry. All those are now off limits because that would change the substance. And then that means we're talking about something entirely different. Okay? All right, so let's go ahead and balance this equation. All right? In order for oxygens to be equal on both sides of the equation, we need to find a lowest common multiple between them. Okay, so the lowest common multiple between O2 and Al2O3, talking about just the oxygen part, would be to have 6 on both sides. And if you're like, could I have gotten it by doing 2 times 3 equals 6? Yep, that works great. Okay. Said another way, there's no way to get these sides to be equal otherwise. Look, I could have like a 2 here, and then I'd have 4 oxygens. But there's no way for this side to get to 4 ever because it comes in chunks of 3. So, said another way, if I put a 2 here to try to find something, that would force me to put a 3 here just to get it to a common number. All right, so there you go. This will get a 3, and then that will get a 2. Redoing our count, 2 times 2 is 4. So we'll need a 4 there, and now this reaction is balanced. All right, we have 4 aluminums on each side and 6 oxygens on each side. Example 2. What happens when you burn hydrogen gas with oxygen gas? You make water. All right, I'm going to put G here because this reaction generates so much heat that the water is going to be initially vapor, gas form. I do realize it'll eventually become a liquid. All right, so there's our product, and now it's time to balance. All right, so here we'll try this method this time. I know some people like it this way. We have 2 and 2 and 2 and 1. Okay. All right, this side is lacking for oxygens. So if I put a 2 here, that will fix my oxygen problem. And it'll create a hydrogen problem, but we can fix that by putting a 2 there. 2 times 2 is 4. And this reaction is done. All right, let me show another way. Okay, we can use decimals or fractions. All right, so rewriting the equation. We get this. 2 hydrogens on each side, 2 oxygens there, only 1 there. So maybe it's easier to balance things by shrinking this side. All right, we could put a half here, and half of O2 is 1 oxygen. All right, or you know, you could put it like a 0.5 there instead. Mathematically, they mean the same thing. And then that way, we would balance this reaction. All right, now, would this be accepted as an answer? My guess is most Chem 101 curriculums will not accept this because of not allowing for fractional molecules, all right? The idea is you can't have a fractional atom or a fractional molecule in real life, so you shouldn't imply that with the math. For me, that's kind of common sense, but I'm just going to stick with the Chem 101 traditional curriculum. So if someone had written a half here, I would just fix the fraction or the decimal by multiplying everything by, in this case, 2 to get rid of the fraction. And then, well, you would just end up with the same answer. All right, so again, feel fractions. Feel free to do fractions as long as if you remember to get whole numbers afterwards. All right, last example. Example 3, we have elemental aluminum being reacted with elemental sulfur. Sulfur is one of the few elements that will have 8 here in its elemental state for the yellow sulfur. All right. So we need to react this. It's going to otherwise be a very similar process to like the other examples where you have elements, they have some subscripts, but really we don't even care about those subscripts. Like here we add an oxygen with a 2 on it, but I wasn't even thinking about that 2 at all in terms of trying to find the subscripts in the products. All right, so in other words, we got to go to the periodic table again. All right, so we have aluminum again, so that's going to be a 3+, and then sulfur is in the same column as oxygen, so it's going to be a 2-. Okay, our product will have those charges, and it looks like we cannot have a 1-to-1 ratio between the elements because that would not be charge balanced. So let's go ahead and charge balance. I like to use crossover to get something nice and quick. And there's nothing I can do to reduce these numbers further, so we have Al2S3. All right. Try to name that for some extra naming practice. All right, it's aluminum sulfide. All right, so sometimes it makes sense to start with the most complicated thing. All right, but yeah, we have 3 sulfurs here, 8 here. Yeah, the only way I see this working is for them to get to a lowest common multiple. And so we do 3 times 8, and then that would be 24. All right, so to get to 24 sulfurs, I would put a 3 here and then an 8 there. Okay, it looks like it was just as simple as like swapping those numbers for coefficients. Oftentimes that will work. You may want to sometimes be cautious in case like you have like an even number there and an even number there. Like it doesn't involve prime numbers or something. If they're divisible, maybe you'd have to reduce those or something. But yeah, the lowest common multiple between 3 and 8 is 24. All right, and then we can check our work on that later. Okay, 8 times 2, that'd be 16. So I'll put a 16 there to get everything equal. Yeah, and again, there's nothing we can do. There's no common number we can find that will divide into these and make this cleaner. Again, said another way, like 3 doesn't divide into 16, 3 doesn't divide into 8, so that reaction is done. Yeah, this might be your first exposure to having really large coefficients, but sometimes that's what you need for the job. I'm going to end this video with some discussion on vocabulary. Earlier in this reaction example 1, we talked about, well, in all the examples, we talked about how in order to get metals and nonmetals to bind to each other, there needs to be a transfer of electrons so that you can make your cation plus anion minus, and you get that nice ionic bond through the attraction of plus and minus. What I didn't do yet, because I wanted you to just balance the equations, what I didn't do yet was show you behind the scenes what's really going on with the electrons. And so we'll talk about that, we'll show that, we'll draw that, and we're going to talk about the vocabulary of oxidation and reduction. Okay. how electrons moved around. So let's revisit this reaction. I'm just going to start on fresh new paper. And again, to review, we had 4 aluminums, we had 3 oxygens, oxygen molecules, and then we formed 2 aluminum oxides. All right, so we recall that at the end of the reaction, we actually had aluminum 3+ here, and we have 2 of them for every 3 O2 minuses. Okay, so this is Al2O3 number 1, but we have 2 of them. So we might as well draw the second one. All right, and in a real crystal lattice of aluminum oxide, you would have a perfect mixing between the pluses and minus to maximize the attractions and minimize any repulsions. But in this drawing, I'm just drawing everything neatly arranged and close to each other, even though it does not really reflect reality. Anyways, 2 Als, 3 O2 minuses, all right? Al3 pluses, O2 minuses. So that is our second aluminum oxide, Al2O3 number 2. 2 of them, so we have 2 of them. All right, but how did it end up being these charges? I think once we've balanced the equation, we can try to come up with a story. You could even try before you balance the equation. So we got 4 aluminums. And then we have 3 molecular oxygens. Okay. Now, if you've studied Lewis structures so far, I know my students have, we would know that oxygen makes these diatomic molecules and that they have double bonds. Okay, but the double bonds, these lone pairs, they're not overly important for what we're trying to demonstrate today. All right, what I want us to do is track the flow of electrons. The only way aluminum will become a 3+ is if it gave away 3 electrons. And the only way oxygen becomes a 2- is to accept 2 electrons. All right, so here's what's happening. Aluminum will give away 2 electrons to that oxygen. Now that that oxygen's happy, the next one is ready for electrons. So we'll give 1 there. This oxygen wants 1 more to become a 2-, but this aluminum's out. So this oxygen's still hungry, so we go to the next one. All right, doing redox often just reminds me of like the hungry, or is it just one hungry? The Caterpillar book. All right, and then so that oxygen's done, and then this aluminum has 2 more left to give, and now that's spent. All right, so we've spent that aluminum, and these 3 oxygens are spent. So that means we've spent exactly half of our aluminums and exactly half of our oxygens. So we should now feel confident that the rest of this should play out perfectly. But just to be sure, all right. All right, so we did the reaction, and here's our before, here's our after. That becomes our first aluminum oxide. And here is our second aluminum oxide. All right. So that's the flow of electrons. Now we can apply some vocabulary. All right, so aluminum became oxidized. All right, that's the terminology. This is how we assign what's getting oxidized versus what's being reduced. Redox. Okay, that's a shorthand way of saying oxidation-reduction. But I suppose redox, red ox, flows off the tongue better than ox red. All right, so redox just means the movement of electrons. All right, in order to move electrons, you're going to have one atom that gives the electrons away, and then you're going to have another atom that accepts those electrons. All right, you cannot have only oxidation, you cannot have only reduction. Both happens at the same time. There's always a giver and a receiver. Okay, so here's the vocabulary. Oil rig. Okay, oil stands for oxidation is loss. It's the loss of electrons. Rig stands for reduction is gain of electrons. Some also phrase it as LEO GER, or as like Leo the lion says GER. All right, so LEO stands for lose electrons equals oxidation. GER stands for gain electrons equals reduction. All right, same ideas between oil rig and LEO GER. All right, so oxidation means to lose electrons. Reduction is what we call it when something gains electrons. This may feel a little backwards. We're used to the idea of, like, if you're getting reduced, if something's getting reduced, it feels like that means it should be losing something. So know that reduction comes from a mathematical sense. All right, here's what I mean. Like, oxidation, you're losing something, and what you're losing electrons. If you lose electrons, your charge number will become more positive. Okay, but why are we calling reduction? Or why are we calling something reduction when we're gaining electrons? We're gaining something. If you gain electrons, the negatively charged particle, your charge number is becoming more of a negative number. Okay, so it's basically because of mathematical ways of describing charge that we're stuck with these horrible terms. Okay, reduction means you're gaining electrons, not losing something. Okay, that's the way it is. Sorry, I know it stinks. But yeah, hopefully this oil rig stuff kind of helps out. Now, some people like to describe chemistry in terms of not what is happening to an atom, but what the atom is doing. Okay, and that's when you call something oxidizing agent versus a reducing agent. That can be confusing, so I'll have a little trick for that as well. First, before we get too ahead of ourselves, let's figure out in our example reaction what was getting oxidized, what was getting reduced. Aluminum was giving its electrons away. It lost electrons. So aluminum got oxidized. And the opposite must be true, that oxygen got reduced. Okay, there's only two elements in a reaction, so we can just do that by process of elimination. But an even better argument is just to see that oxygen is indeed receiving the electrons. We went from a neutral to a negative. Okay, some people will even put like zeros above in the top right of their elements as charges, just to remind themselves that they're neutral. Feel free to do that if that helps you. Okay. All right, so aluminum got oxidized, O2 got reduced. So now I'm going to write this. Aluminum is the reducing agent. and oxygen is the oxidizing agent. Okay. All right, so let that sink in. Aluminum got oxidized, and therefore it's the reducing agent. Did I say oxygen? I'm going to say aluminum. Oxygen got reduced, and therefore oxygen is the oxidizing agent. All right, it might drive you nuts that these terminologies get switched around and they seem backwards. Okay, so let me try to explain that. So we earlier saw that aluminum got oxidized and oxygen got reduced, so that's not new information. The reason why aluminum is called the reducing agent is because in the process of getting oxidized, it reduced something else. Okay, if I'm aluminum, in order for me to get oxidized, I need electrons to be taken off of me. I need to give them away. And because I'm giving away electrons, I am reducing something else. I am making something else gain those electrons that I threw away. All right, and that would be oxygen. Oxygen gains those electrons. Because oxygen is gaining those electrons, it's helping to oxidize the aluminum. All right? So if aluminum got oxidized, oxygen is the oxidizing agent. If aluminum got reduced, oxygen is the reducing agent. You know, the vocabulary almost flows like that. Okay? So which leads to my practical tip. For me, it's easiest to first figure out what got oxidized and what got reduced. And when it comes to coming up with the terms of oxidizing and reducing agent, I just flip the word and then I add the word agent afterwards. I just do that, and that works for me every time. All right, but that's the language of redox. All right, parting note, concluding note, here's a nice little tip. Metals are usually your reducing agents. Or said another way, metals are, I think I said that right, metals are usually reducing agents. All right, they like to give away electrons. They become cations in a process. All right, and then nonmetals are often your oxidizing agents because they can take away and steal those electrons and become negative in the process. All right. The last comment is that oxidizing happens very often. Oxidation happens very often when you're involving molecular oxygen. Oxygen, O2, is probably the most famous oxidizing agent, so much so that the process of oxidation is named after oxygen. Okay, but like if I'm doing some other element, like earlier we had like sulfur here. This sulfur is the oxidizing agent here. It's stealing electrons from the aluminum, but we wouldn't call it like sulfidation or sulfurization or something. It's still called oxidation. Again, oxidation is named after oxygen, but that term oxidation can apply for anything that steals electrons. All right, I think that's enough for this video. Enjoy those combination reactions. All right, thanks. Take care.